In this video, let's look at another example of using Hamilton's method, but also use it as a way of understanding what are the flaws with Hamilton's method and why did the founding fathers eventually choose a different method of apportionment. And then as we go through the next couple lectures, we'll talk about what changes happened, why, and also discuss the idea of fairness and how the change in methodology addresses the problem at hand. But basically, one of the issues with Hamilton's method, and let's just look at a historical example. After the 1880 census, they discovered that Alabama would get 8 seats if the House of Representatives had 299 total seats, but would only get 7 seats if the House size was increased to 300. So what, kind of cutting to the chase of what this is getting at is, let's say they were trying to change the size of the House, or they were trying to determine what would happen using various different numbers of choice. What they noticed is there was a particular paradox that occurred, and it would obviously be a problem. So basically, let's say that they used a house size of 299 total seats. Basically, in that scenario, they calculated that Alabama would get 8 seats with the numbers that they had by using Hamilton's method. But let's say they increased the number of seats up to 300. They noticed that Alabama actually got less seats by increasing the seats. And the issue with the paradox here is they actually are increasing the size in the representation in total by 1, but instead of someone gaining a seat as you would expect to happen, what actually happened is Alabama ended up losing a seat under all of those calculations. And this is what's referred to as an Alabama paradox, just due to the nature of the name, or sometimes it's referred to as I forget the specific name. I think actually this is the name the book uses, if I recall correctly. But basically, like in chapter 1, it's an issue. It's kind of like the monotonicity criterion. If we get more seats, why should our representation decrease? It's not really fair. And we could obviously see how Alabama would have an issue with this, especially if they lost out of representatives. So let's check an example of the math behind an Alabama paradox. We're not going to actually do the actual apportionment in that problem because there's a lot of seats in states and the numbers are quite messy. But let's look at a simplified example. So let's say we were apportioning 200 seats to the following 3 states: Big Sky, Lone Star, and United, with populations as given. So again, to get going, and again, we're going to be using Hamilton's method here because it is a specific method that can have a Alabama paradox. Actually, all the methods we're going to talk about next, it's impossible for an Alabama paradox to happen in those situations. But we're always going to start with, well, what's the total population divided by the standard divisor? So here we have 200,000 people and 200 seats. And that ratio, by cutting out the zeros, would leave us 2,000 to 2, which should be exactly 1,000 for our standard divisor. And actually dividing by 1,000 is really easy because all we need to do is move the decimal place 3 spaces. So the standard quota for Big Sky is always the population divided by SD, right? So I'm dividing by the standard divisor first. And to divide by 1,000, I'm just moving the decimal place 3 spaces to the left in each of those numbers. And that would leave me with the following standard quotas: 9.4, 90.3, and 100.3. And if we're using Hamilton's method, we're going to round the standard quota down, 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 giving us with a 199 as the sum of the lower quotas. Here our surplus is going to be 1, so surp is equal to 1. And who gets it? Well, in this case, Big Sky has the highest residue at 0.4, so they will get the bonus seat and go up to 10. And so our final apportionment will be pretty nice and easy: 10, 90, 100 for a total of 200. And we are done. This would be our Hamilton apportionment. And in these problems, a lot of times what we're going to be looking for is how many objects are they going to get. Obviously, it needs to add up, which it does, and that's kind of our final check to make sure we didn't get messed up in the procedure. Okay, so what is the issue? Well, in that case, there is no issue, but let's see what happens if we actually increase the number of seats to 201. So let's say in this exact same situation, let's say they wanted to use 201 representatives instead of 200. It's not a big difference, and a lot of times the number of representatives might change for various reasons in the Constitution or whatever else. But basically, we're going to have to redo all the math when this changes, because if the number of seats change, the standard divisor will also change, because now it will be, well, what's the total population, to which there was no change, divided by this new number. And this I do not want to attempt to do in my head, which would leave me with a standard divisor of approximately 995. And also, if you're wondering, can I round the standard divisor, or how should I round the standard divisor, it has nothing to do with the rounding method in the system. And technically, you do not want to round the standard divisor at all. But in the case where it's a very large number, or it's, something like this, here I'm rounding it off by 0.02. It's not particularly substantial, but basically you don't want to round it at all. But in the context of actually using it to do calculations, you can round it a little bit. All that will happen is we'll create a little bit of rounding error in your standard quotas, but for the most part, that should not make a big difference unless you're rounding it by too much. So realistically, we don't want to round it at all. You want to use as many digits as you can, but usually it's okay. I'd say, as a rule of thumb, try to give at least 3 significant digits. Don't round it past 3 sig figs. But again, I need to take each state's population and divide by the standard divisor, which has now changed. And notice, since the standard divisor changes, that's what causes the issues here. And since we're dividing by a new number, we're going to get a bunch of new standard quotas. So the standard quota for Big Sky is now 9.44, or 45 if I'm rounding to the nearest hundredth. For Lone Star, it's 90.75. And for United, it's 105. That can't be right. Oh, I divided by the wrong number. So that number didn't seem to make sense based on what I got previously. So let me undo that, and let's redo this calculation using the correct number. And notice it takes a kind of discerning eye to be able to catch mistakes like this, where, it's going to happen, and everybody makes mistakes sometimes, but, every time you do anything, you can think about, does this make sense? Did I mess this up? And that's, I think, how I caught it there, because it didn't look very similar to what I got, when I just did it a minute ago. But anyways, cool. Notice that we get a new set of numbers if we use the lower quotas in each of these. Actually, notice that the lower quota has not changed at all and is still 199. But what has changed is the surplus, which is now 2 seats because we have a total representation of 201. And what also has changed is each of the residues. Notice that actually, if we're using Hamilton's method, the largest residues now belong to United and the Lone Star. And so they would get the surplus seats in this case, and Big Sky would not, leaving us with a total apportionment of 201. Check. Hamilton's method complete. So what's the issue? Well, this is an example of an Alabama paradox, because notice that under 200 representatives, Big Sky would have gotten 10 seats on their house, or again, whatever the situation is. But if we actually increase the total representation, notice that Big Sky actually lost a seat, and that seat was sort of redistributed to its larger counterparts. Is this fair? No, not at all. It's something that's a bad problem. And the issue is in how Hamilton's method works. And really, what the founding fathers and others noticed about this method is that it actually has what's called a population bias. And Hamilton's method is actually biased towards the larger populations, which just sort of means it tends to favor and give more favorable outcomes to the bigger and bigger states in general based on the method. And really the reason why this is happening is because Hamilton's method is focusing on the residue, right? The residue was the controlling factor behind who gets the upper quota versus who gets the lower quota. But the residue is not balanced. While we might think it seems to be balanced on first look, because each state is getting extras based on the decimal value. And decimals are easy to compare, right? 0.4 is bigger than 0.3, 0.75 is bigger than 0.45, and so on. But one of the issues with the decimal is that the fractions here, it has to do with, if we think about what those decimals mean, 0.45, 0.75, 0.880, in each state, it has to do with a much different percentage of their actual population. So let me try to show you what I mean by this. Like in the context of Big Sky, 0.45 has to do with it gives us a particular percentage of their entire population. So if I was thinking about that, and 0.75 has to do with this amount, it's actually easier to see with these numbers. Let's return back to the simpler numbers up here. But when we're looking at the difference between 0.4 and 0.3, that seems like a pretty close comparison. But in the context of Big Sky, that 0.4 corresponded to 400 people, whereas this 0.3 corresponded to 300 people. So obviously this is more people, which means the residue is higher. But if we think about what those people meant on a numerical scale, those are not really an equal comparison. Let's just pretend this stood for 45 people and 75 people. Of course, 75 is more. But in the context of the size of the state, 75 people is a much smaller percentage of their entire population, whereas 45 people is a larger percentage of the population. So whereas 45 is technically smaller than 75, 45 actually represents much more of that population, and really these are not fair grounds for comparison, which this is kind of why larger states tend to be favored with Hamilton's method. And if that didn't exactly make sense, it's probably because this is hard to explain, and it's also hard to really wrap your head around too. But I just wanted you to be aware that there are some problems, and it's not there is a bias here. It's not population independent. Um, and again, kind of looking at the numbers, if I was to look at, well, what is 400 out of the 9400? For Big Sky, that 0.4 represents 4% of their population, whereas with Lone Star, that 300 people that the 0.3 corresponded to was only 0.3% of their population. So even though these numbers seem relatively close, they actually are very, very far apart in terms of the scale of those populations, and very minor population shifts can greatly favor larger states in general. And anyways, that will wrap up Hamilton's method. So for this lecture series, this one's now done. In the next couple videos, we'll be focusing on what are some of the other methods of apportionment, moving on to methods invented by different founding fathers, such as Jefferson, Adams, Webster, who was not a founding father, but maybe should have been. Never mind. I'm just kidding about that. But anyways, we'll circle back to more methods and return back to this issue soon.